Hey there, folks. Let's talk a little bit about what to expect on the test on Thursday. Went over this in class, but let's for folks who weren't there or folks who want to review, let's talk about content. Test. Three. Review. And I'm going to organize it slightly differently than I did before in class, but it's the same basic idea. Let me get stuff out of the way. Okay. So the first of our counting techniques was the fundamental counting principle. And this is the notion that if you're performing a task that has a series of selections, then the number of ways to complete the task is to take the product of the number of ways to do each selection. We did that primarily in 4.2, problems 2, 3, and 6, 7, and 8. But we also did this in ladder sections. This is a fundamental is a good name for it because it's at the basis of a lot of the ideas that we have, even when we're doing things that involve the use of the multinomial coefficient or multi-sets. Still, if it's a kind of a task that has, first you do this and then you do this and then you do this, then you can still use the fundamental counting principle to kind of tally up how many of those things are by just multiplying those numbers. Okay, so this never truly went away throughout all the counting that we did. If we are looking at an ordered selection, of our things from n possible items, with unlimited repeats. And really what I should say here is, well, the fact that it's an order selection kind of says this, but possible is not really even, possible is kind of goes without saying. The real word I should use here is distinguishable, things I can tell apart. So I think I'm going to go with that. Okay. With unlimited repeats, then you've got different slots here, and you've got R slots and N choices for each slot. So that's where you get the N to the R. Okay, and we did some counting like that in those same problems, 2 and 3 and 6 and 7 and 8. And really that's just an application of the fundamental counting principle. When we look at an ordered selection of R things from N, and I'm going to do it right this time, distinguishable items, with no repeats this time, then these are permutations n pick R, which is just n factorial over n minus R quantity factorial, which is really just the, again, the fundamental counting principle. You've got R slots here, and n choices for this one, then n minus 1 for that, n minus 2 for that, and on down the line. Okay? So ordered with unlimited repeats, ordered with no repeats, and now unordered, collection I'll call it, of R things from N distinguishable items with no repeats, and these are combinations in choose R, and a lot of times we use this binomial coefficient notation, but it's just n factorial over r factorial times n minus r quantity factorial. Okay. The permutations really was just a further application of fundamental accounting principle. I think we used it in 7 probably. The combinations actually popped up in 4.3 in problems 5, 8, 9, 10, and 11, plus latter sections when we started to talk about counting multisets. We changed that multiset notation into a binomial coefficient, right? Okay. So ordered with repeats, ordered without, unordered without, and then we got into ordered again, but with fixed repeats. And ordered selection of in distinguishable items, but with some repeats, okay, and a fixed number of repeats. Then that involved the multinomial coefficient, and this is where you got n things that's actually not right. That's length. Let me say this right. Length n. I don't want to get into the distinguishable business on this one. Of length n, but with fixed repeats of some items. And so here's where you list kind of the, R1, R2, and you just have to make sure Rn where all those things add up. K is better. R sub k, they all add up to n. Then this gives us just n factorial over R1 factorial, R2 factorial, on out to R sub k factorial. Okay. Oops. There we go. Okay. And then from that point on, and let's see, we did things like this in 4.4, problems 3A, 4, 5, 8, looking at words like Tennessee and saying, how can you rearrange the letters in that? Okay. But everything else that we did involved multisets. Unordered collection of size k from n elements with repeats. And this is the n, and we say multi-choose n. And this comes down to our stars and bars representation, right? If it's of size k, then you got k stars, and the only way you distinguish between things being one element or another element is you put a bar in between them. So with n elements, you would end up with n minus 1 bars. So this is k stars plus n minus 1 bars, and then you just have to pick the location of the k stars. Okay. These are called, by the way, multisets. And we looked at things like this in 4.4, problems 3b, 6, 7, 9, 13, and 15, and also in the supplement, problems 2, 3, and 4. Okay. And then we talked about what I call at least multisets. This is where you put at least so many of each element in the multiset, and just count the number of ways to complete it. So I think one of our examples was, a box of donuts out of 10 types, box of a dozen donuts out of 10 types, but you have to have at least one of each of the donuts. So you go ahead and put those 10 donuts in there. That leaves you with 2 spots left. And so you've got 10 things to choose from. You want a multiset of length 2 at that stage of the game. And so you just work that out. But the idea behind the at least multisets is that you just go ahead and put them in there. And then what we did for today, at most, can't spell today, multi-sets. We did this using the inclusion exclusion principle, which means that you to calculate a intersection of a bunch of complements. I didn't mean to put a K there. Then that's equivalent to the number of things in the union complement, the complement over the top of the entire union, which is just all the things in your universal set minus all the singles then plus the doubles, A1 intersect A2, and on out till you get all the pairs, K minus 1 and K, and so on. So the next one actually would be minus, and you keep doing this until you get out to the end where you've got until you've got all the intersections. Okay, just keep alternating that sign as you go from the intersection of size 1, intersection of size 2, and on. Okay, and we did that actually. We did the at least multisets in the supplement problems 1, 3, and 4. And then we did the at most multi-sets on the supplement with problems 5 through 9. Okay, so your test will look like those homework problems, really. These at most a lot of times require a bit of work. They're not hard to follow perhaps, but they do take some time, so that's probably a page problem. And then 2 or 3 problems per page on the other 3 pages. Just want to get a thorough covering of all these different counting techniques and make sure that you can do them. And fair mix of that. I will caution you on the test, even though we're dealing with numbers now, don't forget to explain yourself. If you make a mistake and I don't have some way of understanding why you did what you did, it's very difficult for me to come through then and give any partial credit. If you've explained yourself and it was just a mechanical error or you looked at the wrong number or something like that, then I can, minimize the amount of points that I deduct. But I need to understand what you're doing, okay? So please do talk to me a little bit in writing on the test about what it is you're doing, and then carry out the work. Okay, that's it. That's what our test will look like on Thursday, and we'll see you then. I'll try to get there about 15 minutes early. Let us start